Okay, thanks very much. I am part of the GraalVM project at Oracle Labs. My research background is exclusively in the area of tools that people use, debuggers, stuff that people look at and use to get work done, which makes me not really very much of a VM guy, but somehow I keep landing in VM-oriented groups, trying to make a contribution in the space of tools. Here's a group photo that was taken in 2015 of an all-hands meeting, and the guy with the hat is the tools group. That would be me. And until a few months ago, I was the one person really focused exclusively on tools in this VM. It's a very, well, actually first moment for the lawyers. So here's the GraalVM execution stack architecture, and this is very much my personal view. This is stuff I care about as opposed to other people. For me, the single most important thing starting up was this is a platform for implementing lots of languages. So there's leverage if you're a tool builder. Maybe we can take tool technology and make it apply to multiple languages, as the GraalVM folks have for their stuff. It's based on an ASD execution model. I'll say a lot more about that. The fact that the execution model is kind of comprehensible to mortals like myself means that perhaps we can also leverage that in the construction of tools that would make sense to guest programmers. So in that sense, I'm a proxy for guest language programmers. It gets even better though. This is very much a performance-focused VM, and the fact that they've got very aggressive optimization in the platform, and crucially for me, the optimization, which was in fact, many of you probably know, was invented exactly for debugging purposes. So it's part of the platform. And it's all in Java. So the host language is Java for implementing languages, which means we have the opportunity then to build tools in a uniform sort of way in the host language for the runtime. And so let's see, did I mention performance? This project is all about performance. So when Stefan asks whether it scales, I'll have an answer because that's mainly what I'm going to talk about, is how a tools person sort of managed to survive and get useful work done in a very, very high performance VM. We could call this the clash of civilizations between people who want to build debuggers and other tools and people who want super fast runtimes. It's taken a lot of patience and negotiation and collaboration, I should say. So it's fast, it's comparable. We have implementations that are comparable to good specialized implementations. Those are the four on the outer parts. We also have very, very effective implementations of a couple of languages that are notoriously hard to optimize, not really in R. And the people in this room will know about that, Adam in particular. So enough about that. So what did I decide to do? I wanted to go for generality, not just for multiple languages, but sort of to make it possible to build lots of tools, not just debuggers. Let's try to open up the VM in such a way that we can actually innovate and build tools, maybe some kinds we haven't thought about yet, maybe the kinds that used to require that you go on and modify the VM for your experiment, but it would never reach production. Let's see what we can do. So the first thing is look at the ASD execution model and actually expose events that happen in execution state. And I'll say a little bit more about what I mean by events, other than the observation that they're sort of natural in the case of an ASD interpreter. And to open it up, in other words, basically we need an API. So let's create an API in Java, in the host language, so that we can actually have a tool that talks via Java API, gets access to that state and those events. If we're going to build polyglot tools, then we're going to need a little bit of support from individual languages. They don't all actually operate the same from the standpoint of a debugger or other tools. So there is an extension of the API that the language implementers use, where we ask for some additional information that makes it possible to kind of gloss over differences, and we'll see a little bit more of that in the future. And did I mention performance? Okay. Strategy is then take the instrumentation code and make it look like guest language code so that the optimization people will optimize it without knowing the difference between instrumentation code and guest language code. So sort of it's a martial arts blend. If you sort of pretend that you're part of the runtime system for the languages, then you'll actually benefit from all the optimization. So the instrumentation framework, we code it kind of according to best truffle practices as if it were part of the language implementation. And finally, an API so that you can actually create a tool or an instrument, as we call it, that gets loaded alongside our execution engine and then gains access to events. Okay, something about the execution model. I mentioned the AST interpreter idea. This is the tool-oriented person's view of execution with respect to how do we get access to executions. Well, in the slow path, we're running like an ordinary Java interpreted AST. Life is great, okay, because all the actual execution state is represented explicitly in Java. Okay, there's a frame, there's frame slots, there's a stack, and there's APIs for that. The same APIs that the language implementers use themselves are accessible to tool building. So this is a free lunch if you're a tool builder. It means if you're inside Java and your program is halted and it's an AST interpreter, it's all right there. It's just an API away, all Java objects. That's the slow path. Okay, probably some of you who know that the first thing that line of optimization within the Truffle Growl framework is ASTs are constantly rewriting themselves. And that's sort of the first thing that happens. They specialize themselves, but they're still ASTs. So from my perspective as a tool builder, it's still an AST. Life is easy when they specialize themselves. The specializations include guards, but pretty straightforward stuff in the simple cases. There's a lot of specialization boilerplate code that's really useful for you implementing your language. I don't worry very much about that. It doesn't affect me too much. Okay, when things really compile into the fast path, things get a lot more interesting, and this is really where the Truffle and Growl platform shines. The Truffle code is designed to be very easily optimized by the Growl compiler that uses partial evaluation. You can explicitly manage assumptions. Assumptions are speculations, if you will, that the runtime system uses to optimize and eventually de-optimize. But as a tool builder, you can actually play that game as well. You can say, assume that this is constant until further notice, that will get partially evaluated, will get compiled away, and that gives us a lot of advantages for dealing with performance issues. The best free lunch yet is the fact that if you're writing tools and there's information you need that simply disappears in the fast path, well, you can explicitly de-optimize when you need to. So again, back to the roots, okay, back to when Rose built the optimization itself. You basically need to debug. You just basically said, let's just recreate the AST interpreter without loss of execution state. So those are great opportunities if you're a tool builder to sort of work in that platform. So let's say a little bit more about how you do that, how you actually get those hooks in, and then I'll mention sort of the overhead, how we're able to get away with getting stuff in with relatively low overhead. So again, I've said that all I really have to do is deal with the AST model of execution, relatively straightforward. So let's imagine that we want to capture events around a particular node, and imagine that it's a statement, okay, something relatively straightforward. The kind of events you care about really are, well, I'm about to execute this statement. This is where a debugger might want to halt, or maybe I just returned and there's a value, or maybe there was an exception thrown. Those are exactly the three events that you might want to capture. The Truffle style of programming, the nodes tend to each do a very simple thing, and so that leads naturally to events that are easily understood. So what do? Well, okay, if we want to capture those events, we do what Truffle does, we rewrite the tree. Okay, so core function of the platform, I insert a wrapper node. The wrapper node is language specific because it acts as a proxy for its child. And so we need a little bit of help from the language implementer. We can say, can you give me a wrapper node for this child? It's relatively simple in most cases, and its job, in addition to proxying for the child, is that it reports these events that I described. So to whom does it report? Well, I've attached another node, and again, it's an AST node. It's the same technology that Truffle uses. It's purely an instrumentation node now, and it actually manages the propagation of events to interested parties. And it takes care of what we call subscribers, and so I'll say a little bit more about that now. Subscriber basically is somebody interested in, a tool interested in hearing about events in that particular node. The first kind of subscriber simply listens for events. Okay, we're about to execute this, we just did, here's the value, or an exception was thrown. So we add another node. Okay, this is a subscriber node, and this particular subscriber node is responsible for also for propagating events, but its main job is to call the listener for its client. Notice the dashed line here. The dashed line suggests that we've changed kind of out of the AST framework now. This is a call out to something that's not a node. That changes the game a little bit with respect to optimization. I won't go into any details there. When you implement this stuff, there's a little delicacy there of what gets inlined, what doesn't, and there's some stuff you have to pay attention to. But if you play that game well, this stuff can run really, really fast. The way the subscriber model works is you can have multiple subscriptions that happen to relate to a particular node, perhaps for different reasons, and they simply get dispatched by these nodes again. And all this framework code is handled by AST nodes, again, subject to all the same optimizations in the fast path. How do you subscribe? Okay, so again, try to be as general as possible. There's a way you create a query that applies to some subset of the nodes at runtime. And if you add new nodes, you compile new methods, then the subscriptions will apply to those dynamically as well. It's easy to say line 42 in a specific source, for example. You can imagine why you might want that query. But there's another query for debugging. You might say anything marked as a statement. And I'll say in a moment what it means to be marked as a statement. It's relatively straightforward. You can add as many subscriptions as you want dynamically. You can have them, take them away. Adding them is bed safe. You can actually come to a running program and you can sort of add one of these things and it will take effect. Subscribing and unscribing, as you might guess, is in general a de-optimizing event because it rewrites the tree, and that's where it gets interesting. It's lazy, however, through explicit use of these things called assumptions, which is a first-class object in this framework that we can use to manage what we do. When you create a new subscription, this involves kind of scanning over all the code you know about and flagging assumptions as invalid. And for things that involve specific sources, you can exclude most of them by simply looking at the root and say, that's not the same source you care about. And you invalidate that, but it's lazy. Nothing happens until such time as execution reaches an event where the subscriber set has changed. So it's relatively low overhead to sort of say, let's start stepping, let's set listeners on every statement. That keeps the overhead low, even if something is potentially complicated as deciding to step in a program that's fully optimized. There's another type of subscription. This is the second of the two types, and this one is a query plus an AST factory. So here's back to our previous scenario where there's one subscriber of the first sort who's simply listening for events. An AST factory actually invites the subscriber to, on first execution, to provide an AST. Give me a fragment of AST. And the framework will say, okay, once it has that on first execution, it will essentially plug it into the AST. It becomes part of the AST. This goes back to Urs Hölzler's technique for simply adding a breakpoint by rewriting the program. And you add a conditional breakpoint by rewriting the program with a condition expressed in the guest language. Anything in Truffle Grail that's expressed as guest language AST nodes is subject to full optimization. So this is a great way to do breakpoint conditions. So the subscriber node here will actually execute that AST fragment each time execution comes by. And it will do that in the context, the lexical context of the node that you've instrumented. That's why you have to provide a factory, because the client has a fragment of code, but you'll need to essentially compile it into each location, which again happens lazy. So this is how you do a breakpoint condition. And again, the upshot of this is that a breakpoint condition will be compiled in the fast path as if it were simply part of the program. So a lot of performance to be gained there. Okay, and again, they're orthogonal. You can add multiple subscribers. They tend not to interact unless one of them decides to halt the program. And so the idea is to be as flexible as possible. I've used debugger as my example for this low-level stuff, but in fact, you can build a code coverage tool pretty straightforwardly with this. We're working on a profiler that uses this at the low level. And I happen to know, and I'll mention some other clients who've been using the low-level instrumentation code for other things as well. So what do I need from language implementers to make this work? Because the framework itself is language agnostic. I prototyped a debugger and some other tools, multi-language debugger. So if you're running, GraalVM with multiple languages, the debugger just works. But how do you make it intelligible? These are the things we've come up with so far. I've already mentioned marking the node. So there's basically what I call markup, where metadata needs to be present. The first one is source attribution. Okay, so we put a pretty strong stake in the ground that says you really have to know which nodes correspond to what source. Now, there's a lot of other nodes that don't really correspond. They're implementation artifacts, but the ones that matter, where execution would halt and a guest language programmer would actually understand what's going on, they get marked by the language implementer. They're symbolic, statement, expert. These are the ones that the debugger will use to configure its behavior. Basically, whatever the language implementer says the debugger should treat like a statement, the debugger will treat like a statement without knowing anything else. Visibility is important. There are often frames, there are slots in frames that are actually implementation artifacts that don't correspond to the guest language. So the language implementer just tells us that. If this particular frame is internal, just don't show it when you're showing the stack trace. That's all I really need because there's a standard internal API in Trouble for getting the current stack. Okay, so I don't have to do any mapping. I just get the stack. And I might discover that some of the stack frames were implemented by some language or part of another language, but they're all essentially implementing the same internal APIs, and I have access to them the same as any language implementer. So no stack mapping, no magic. All I need to know is which ones to hide. Presentation, yeah, there's some things in a simple debugger you need to print out. So I mentioned values. Clearly, if you want to say just print a value, print a method name, there's some methods there. There'll probably be more of those as we get more featureful, but right now it's a pretty small set of things we need to sort of print out. I'm not going to talk much about object inspection right now, other than to say that there is sort of a common object model that's under development. So to the extent that that gets used by language implementers, we'll be able to piggyback on that with an object inspection facility. There's a partial implementation that in place. I'll say something about that. Okay? All right, so a couple of other things I mentioned before. Let's see, I'm out of time here, so I'm just going to say that if you go from left to right, when you turn on, for our step, you can sort of enable debugging, no overhead. You can sort of add instrumentation, no overhead. In the case of Ruby, these explode. You get an order of magnitude every time you change one of those things. You might add something, set trace function, famously, if you know Ruby, it's very expensive. When you turn it back off, the overhead goes away completely. So total disappearance of overhead. Okay, and we've used it for a lot of different things. With debuggers, profilers, counters, we're working on that. We use it for time boxing. You can just sort of say all of a sudden halt. There's some external collaborators who've done some interesting tools. I hope we get more. To the extent that there's been work on concurrency doing that, Stefan is the person who's probably done the most there. He can answer questions. So with that, I will acknowledge all the people who contributed to the platform, several of them are in the room, and I'd be happy to take questions. Yes?
You say that one of the conditions the language implementer is to know which nodes correspond to the source code. But
yes.
If it's node rewriting, how do you know the source code?
Generally, that's a good question. Yeah, there are cases where language implementers throw nodes away. In general, when the nodes rewrite their implementation nodes, and so they tend to be stable. Okay, so we find that the important nodes that the user would care about tend to be stable. But it is a constraint. So we've actually had one bug where an empty block, got noded away. But in general, if that will show up as a language implementation bug, and we might encourage them.
But is it always possible?
Yeah, it is possible. We haven't run into any cases yet where the nodes were rewritten in such a way that we lost track of the statements. Yeah, Hans?
Hi, Michael. You mentioned that it's a challenge when it comes to inlining, since you add all these ASP nodes, that inlining may produce different optimized code and it may make different optimization decisions. So what's the challenge for your runtime? Would it be possible to get these heuristics, to give them an API, to make them aware of the debugging ASP nodes so that they would produce the same optimized
We haven't needed to yet. So what we've confined ourselves to, in a sense, we're acting as if we were part of the language implementations, which means that in the fast path, there is some information you can get in the fast path. So we make do with that. And if we need, for example, like the expression evaluation, we write it in as if we're part of the source code. And that's going to be in the fast path transparently.
Well, there's actually a little bit of an API. So for those nodes, you can associate the cost, and you can actually say, okay, that's an instrumentation node, and we say it has no cost. So then at least some of the inlining heuristics ignore that.
Yeah, I guess that's critical as a VM implementer if you're looking into some problem to get the very same with and without debugging.
Yeah. So the nodes, for example, that propagate events, those are very simple methods and they get flattened out completely. And in the Ruby chart that I didn't have time to show, it sort of demonstrated that even if you have a lot of instrumentation installed, if it's not actually doing anything, it will be inlined away from Lily. And until you actually do some work, it has 0 again. So that's the way, is not to ask anything of the VM, but to simply play by the VM rules.
One quick thing, who's the next speaker? Ah, okay. Yeah, we still have time for questions.
Yeah, please. More questions? No more questions?
I actually have a question.
Yeah, Adam.
If I may. So it's obviously great that you can put in the support and can say put the breakpoints in, and if it never get hit, then the program gets optimized at some point and runs full speed. But in the actual debugging scenario, so to speak, when you actually are doing something, how well does it, or how well do you expect this will work? For example, there is this example where you have parts of ASTs that are being plugged into the main program that represent breakpoint conditions. If you start hitting those conditions, though, you'll have invalidations, right? Because you will have to break into the debugger, and then portions of your program
Yes.
get invalidated.
That's right.
And then the heuristics to recompile them again are such that it takes a long time for those to be.
So there is a disconnect. Yeah. Once you're stopped and you're starting to step around the code, you're going to be de-optimizing a lot of code.
I was wondering if you have a feeling on whether you sort of, the performance factor is as important there as it is when you're actually sort of waiting for the debugging events to happen.
I would say we don't have a good feel for that yet. In a sense, we've been optimizing for 2 cases. One is the slow path where you really want access to everything. And the other is where you have conditions for long-running bugs that you want them to run fast with conditions. In between, I don't have a good feeling. Stefan?
I have a good feeling it's awful. it's effective housing or something. So you really feel it every time.
So is there anything you think could be done to, like maybe temporarily change heuristics for inlining so that you can actually kick in the compilation faster for those cases when you actually, you hit the breakpoint, change the condition, for example, but you want to recompile it quickly so that everything goes faster as well.
I think you asked our team people to check for the interactive REPL that actually the heuristics are lowered so that it's not up to
Because that could be a solution for the middle ground. But I know that it has to be just used more and more and more.
Yes, and
it'll be improved more and more.
And I have to say, Stefan is probably the heaviest user of this.
We still have 5 minutes for questions.
Yeah.
So, if you still want
I'll point out there is work going on for replay compilations, and so when that's done, it will be possible to say, okay, if we de-optimize this thing, let's just re-optimize it using the same kind of parameters when it was originally optimized, and we get back to this performance we had before.
Right, but what would be nice for interactive debugging is that there is a higher urgency. So if you have an interactive debugger attached that you want to re-optimize.
Yeah, that's what I'm suggesting. Maybe we could hook into that so that after you made your change and hit continue, you trigger basically the same compilation that generated the code before, except with a change that you made, and you're back to that performance again.
So I have one question that's more general, and I'm not sure you have an answer for that, but what about non-local transformation and non-local instrumentation? So, I mean, the API at the moment is very much for one specific AST node.
Yes.
But I have from the lead that I actually need to coordinate multiple AST nodes.
Don't have much to say about that. So your experience with that is probably revealing.
Except my feature requests.
Yes. Well, my feature requests get ignored as much as yours, let's just put it that way. This is back to the Clash of Civilizations model, where it's very hard to get features in. There's a lot of patience and negotiation, and it's not always a priority. It's a fact of life. So that's what I've been working on for a while.
Okay, one last question? No? Then let's say
Okay.
Michael.